Unmute. You need to unmute him.
Test. Okay, I think my audio is up. Thank you everybody for joining today's webinar. My name is Drew Barbier and I'm the Senior Product Marketing Manager at Sci-Fi. Today I'm going to be giving an introduction to the RISC-V architecture. This webinar is targeted at embedded developers who want to learn more about RISC-V. In it, I'm going to cover the RISC-V instruction set, privilege modes, and interrupt architecture. At the end of this presentation, you should have a basic understanding of RISC-V fundamentals and know where to find more information. This is the first in a three-part webinar series. I'll be giving the second part on May 15th, where I'll be going into more detail on Sci-Fi's 2 series of RISC-V Core IP. And then the final webinar will be on May 23rd, where I'll go from customizing a Sci-Fi 2 series core using Sci-Fi's Core Designer web-based tool, all the way to Hello World and using some of Sci-Fi's software development tools. You can register for the next 2 webinars using the URL below. This is a live webinar and I do have some coworkers standing by to answer questions live. You can ask questions by clicking the question and answer box at the bottom of your Zoom window. At the end of the webinar, I'll field a few questions live as well. We'll start off with an introduction to RISC-V. First off, it is pronounced RISC-V, and it started as a 3-month project in 2010 at the University of California, Berkeley. 2 graduate students, Andrew Waterman and Yunsep Lee, and their professor, Krista Asanovic, needed a simple instruction set architecture which could easily be extended. They found that the commercial instruction set architectures were too complex and also presented IP legal issues. So what is RISC-V at a high level? It is a high-quality, license-free, royalty-free RISC instruction set architecture. It is a standard which is maintained by the nonprofit RISC-V Foundation, and it's suitable for all types of computing, from microcontrollers to supercomputers. The RISC-V architecture is available freely and under a permissive license. RISC-V is not, however, a company or any specific CPU implementation. The RISC-V Foundation governs the RISC-V architecture and is a nonprofit organization which was formed in 2015. The RISC-V Foundation has 3 primary functions, and that is to direct the future development of the ISA. It is also to develop compliance tests and suites for the RISC-V architecture, as well as promotion of the architecture at industry events and marketing. The RISC-V Foundation has greater than 230 members representing a wide range of markets. So you can see we have a number of members from the semiconductor industry with members such as Qualcomm and Samsung and Marvell. There's also representatives from the software companies with companies like Google and Imbacosm, tool and enablement vendors with companies like Seger and Lauterbach and IAR and Antmicro, and IP companies like Sci5 and Rambus and Ultrasoc, and much, much more. In the RISC-V Foundation, there are a number of specifications. The two main RISC-V specifications are the user mode and privilege mode specifications. The current version of the user mode specification is at version 2.2. The user mode specification was frozen in 2014 at version 2.0. And since 2.0, there have been some minor updates, such as moving specific CSR and fence instructions out of the base user instruction set, and also some clarifications on the memory model. The RISC-V privilege mode specification was just ratified at version 1.11. And then the debug specification as well was also ratified at version 0.13. In addition to these main specifications, there are a large number of additional specifications also in progress. Some major notable ones would be the hypervisor extension, which is currently in version 0.3 draft, and the vector extension, which is at 0.7 draft. And then there's many, many more. I do encourage everyone on this call to participate in the RISC-V Foundation. You can go to RISC-V.org and sign up for the mailing list. You can also become a member of the RISC-V Foundation and actively participate in the future of the specification. Now let's start with some RISC-V basics. RISC-V uses a standard naming convention to describe the ISA supported in a given implementation. And that ISA naming convention has the format as follows. So RV, which stands for RISC-V, and then a sequence of numbers, which can be either 32, 64, or 128. This number indicates the width of the integer register file and the size of the user address space. Then following this number could be a sequence of letters, and these letters are used to indicate the set of standard extensions supported by a given implementation. So extensions define the instructions supported by an implementation. And for all RISC-V implementations, the only required extension is the I extension, and I stands for integer. The integer extension defines a set of 40 instructions. And then the RISC-V specification itself also defines a number of what it calls standard extensions. Standard extensions are extensions which are defined in the RISC-V Foundation. I have some examples on the right. So the M extension defines hardware multiplication and division instructions. The A extension defines atomic instructions. F and D defines the single and double precision floating point. And then G is sort of a shorthand that stands for general purpose. And it is the I, M, A, F, and D extensions combined together. And then the C extension defines the 16-bit compressed instructions. And I'll touch on all of these as we progress through the webinar. One of the great things about RISC-V is it allows for easy and modular customization, in that it allows you to add your own custom instructions. Now you can indicate this in your implementation using the capital letter X in the ISA string to denote your custom non-standard extension. And so if we put this together, I have a few examples of legal architectures. So you can see RV32I, which would be the most basic RISC-V implementation. And you have RV32IMAC, which implements the integer multiplied, atomic, and compressed extensions. RV64GC, which would be the 64-bit I, M, A, F, D, and C extensions. And then I have a non-standard extension example as well. The RISC-V register file defines 32 integer registers. The registers also have an optional 32, there are also an additional optional 32 floating point registers if you implement the F and D extensions. There's also another standard extension called RV32E. RV32E introduces a reduced register file where only 16 integer registers are implemented. And this is primarily for area-constrained embedded devices. The width of the registers are determined by the ISA. And the RISC-V architecture also defines the application binary interface that software uses to communicate with itself. On the chart on the right here, I have the register names as well as their ABI names for specific ABI functions, as well as whether a particular register is callee saved or caller saved. RISC-V privilege specification defines 3 levels of privilege, which we call modes. This would be supervisor mode, hypervisor mode, and machine mode. Machine mode is the highest privilege mode and the only required mode in implementation. And this flexibility in modes allows for a range of targeted implementations from very simple microcontrollers all the way up to high-performance application processors with support for virtualization. Machine, hypervisor, and supervisor modes each have their own control and status registers, and I'll cover these at length later. Let's take a look at some RISC-V instructions. And we'll start with the reference card. So the base I extension with the 40 instructions are noted on the left here. Implementing the privilege modes adds several additional instructions for accessing CSRs and changing levels. The M extension implements several more hardware multiply and divide instructions. The atomic extension adds additional atomic read, modify, write operations. And then the F and D extension implement hardware floating single precision and double precision floating point instructions. And then the compressed extension implements 16-bit equivalents of the base integer instruction file. Now, one thing that's neat about RISC-V is that it's the same instruction set regardless of the machine width. So these instructions apply to 32-bit and 64-bit implementations. And so we'll start with compressed instructions. So most of the basic integer instructions compress. That is, they have 16-bit equivalents. And the reason why you might want compressed instructions is for smaller code size in embedded systems. So in embedded systems, typically these devices are dominated in cost by the amount of flash and RAM on a device. So the smaller the more dense your code and data, the smaller your memory requirements are and the lower the cost of the device. Smaller code size can also increase performance and reduce power. And specifically, we're talking about better utilization of cache RAMs. So if my instructions are half the size, then I can fit twice as many of them in my caches. And this results in fewer transactions across higher power interfaces like DRAM controllers. Now, as I mentioned earlier, one unique point of RISC-V is that the 64-bit architecture can also use the C extension. And that is specifically, you can have a 64-bit architecture with 16-bit instructions. And if you look at the code size comparison between RISC-V using the compressed extension for the SpecInt 2006 benchmark, RISC-V is very competitive with the equivalents. And especially if you look at 64-bit architectures, it's quite a bit smaller than all of the other architectures because it supports 16-bit instructions. The atomic extension allows for atomic memory operations. And these are operations which perform read, modify, write in a single instruction that are guaranteed to be atomic. In the atomic extension, there are instructions for logical operations, arithmetic operations, as well as swap operations. And there's also low reserve stored conditional pairs. On the right here, you can see an AMO swap instruction, which we're using to directly implement a spin lock. So the first swap instruction is to gain the lock, and the second swap instruction is to release the lock. RISC-V also implements fence instructions. Fences are used to enforce a program order on device I/O and memory accesses. And that is, all operations that happen prior to the fence are guaranteed to complete prior to the operations after the fence. Now the fence can be a pretty costly instruction from a performance standpoint. So it gives you granular control over which operations you want to observe, both before the fence and after the fence. So you can specify whether or not you want read operations to be observed or write operations or read and write operations and so on. And so the equivalent of a full barrier in RISC-V would be the fence RWIO, RWIO. And this would wait for all read, write, and IO operations prior to the fence to complete prior to any read, write, IO operations after the fence. CSR stands for control and status registers, and these have their own dedicated instructions. And this allows you to read and write these registers, but they're also useful instructions for read and set bit and read and clear bit. So you can set and clear bits in a single instruction. RISC-V also defines environment call instructions to transfer control to the execution environment. And this is typically used to move up the privilege level stack. So if I wanted to go from user mode to supervisor mode, I can use an eCall instruction. And you'll see this a lot in application software where it's calling into, say, the Linux kernel or into an RTOS kernel. So now let's take a look at some of the RISC-V control and status registers. Control and status registers are registers that contain the working state of the RISC-V machine. CSRs are also specific to a mode. So machine mode has about 17 CSRs, not including the performance monitors. Supervisor mode also has a similar number of CSRs. Most of these are subsets of the machine mode CSRs, although some are unique, and we'll touch on one or two of those a little bit later. The CSRs are defined in detail in the RISC-V privilege specification, but we'll cover a few here as well. There are a number of identification CSRs, the first being the machine ISA, and this is where you encode the ISA string that we talked about earlier in the register file so that software can interrogate this register and understand the exact implementation that it's running on. There's also a machine heart ID, where heart stands for hardware thread. You can think of this as equivalent to a core. So this would tell you the heart ID number that particular software is running on. And then there are additional vendor and machine IDs that can further define the exact implementation of the design. Machine status, or MStatus, is the most important CSR in RISC-V. So there are a number of bit fields here that have to do with interrupts. I'm not going to cover them here as I cover them in detail a little bit later. There are also register fields here that tell you the previous privilege mode. So this is read-write fields that you can encode, that you can write to go down a privilege level. It also tells you the privilege level that you came from. And then there are a number of state registers as well, which tell the machine something about the state to allow software to understand the environment, whether or not it needs to save registers and so on. There are a number of other registers that affect the execution in machine mode, allowing machine mode to access memory such as it was a lesser privilege mode like supervisor or user. There are a number of other registers as well that have to do with virtual memory and trapping S returns and things like that. There are timer CSRs as well, so mtime. So the RISC-V architecture defines a requirement for a counter to be exposed as a memory map register. This is a 64-bit timer, and there's no frequency requirement on the timer, but the specification does say that it must run at a constant frequency, so the frequency of the timer cannot change, and that the platform must expose this frequency to software. And this can be something as simple as a hardware header file. There's also the mtime compare register, and this is the register that you would use to generate a timer interrupt. So you can write a value into the mtime compare register, and the machine should trigger an interrupt if the value of mtime is greater than or equal to mtime compare. So I mentioned earlier that specific modes in RISC-V have their own CSRs. Well, most of the machine mode CSRs have supervisor mode equivalents. And supervisor mode CSRs are used to control the state of supervisor and user modes. So just like we had MStatus, there's also an SStatus equivalent. And then as far as interrupts are concerned, STVec, trap vector, and interrupt pending and interrupt enable are all mirrored in supervisor mode. And I'll talk about those registers in the interrupt section. There's also an additional CSR in supervisor mode, which is not in machine mode. And this is the SATP CSR, or Supervisor Address Translation and Protection Register. This CSR is used to control supervisor mode's address translation and protection. So in RISC-V, virtual memory is supported in supervisor mode only. And so virtual memory, it provides a mapping of address space from the physical address space to some virtual address space. And this is typically used to ease the burden of software development to provide a consistent hardware environment. And you'll typically see virtual memory supported in operating systems like Linux. So as I mentioned earlier, virtual memory requires an S-mode implementation. And the virtual memory architecture, the RISC-V ISA defines several different versions of that, depending on the width of virtual address space that you need. So SV32 is a 32-bit virtual address space. SV39 gives you a 39-bit virtual address space, and this requires a 64-bit implementation. And then SV48 gives you a 48-bit virtual address space, also requiring a 64-bit implementation. And as you would expect, the page tables in RISC-V's virtual memory architecture also contain the access permission attributes for a given page table. So whether or not that page in memory is accessible by lesser privileged modes and what the exact permissions are. The RISC-V privilege specification also defines physical memory protection. And this can be used to enforce access restrictions on lesser privileged modes. So in this way, machine mode can prevent supervisor and user mode software from accessing unwanted memory regions. And the specification defines up to 16 regions with a minimum region size of 4 bytes. So in the example on the right, I have an example memory map, and you can use the first region to mark the entire address space as not accessible to user mode, and then use the additional regions to map in specific contexts that you want user mode software to be able to access. And in that way, if user mode software tries to read, write, or execute address space outside of those windows that it's not supposed to, software will then trap to machine mode, where then your software can then make a determination on what to do next. Another neat feature of RISC-V's physical memory protection is the ability to lock a region. When you lock a region using the PMP, it enforces access permissions on all accesses to that memory region, including in accesses from machine mode. In this way, machine mode can lock a section of memory, and that memory would be inaccessible to any software regardless of mode. And the only way to reset a locked region in memory is to actually perform a system reset. Now let's talk about interrupts. RISC-V defines the following interrupts per heart: software, timer, and external interrupts. Software are architecturally defined software interrupts. So this is an interrupt that can be used for interprocessor communication, for example, writing to a register which can trigger an interrupt. Timer interrupt uses the mtime and mtime compare registers that we talked about earlier. And then external interrupts are for peripheral interrupts. These are normally where most of the peripheral device interrupts, such as DMAs and UARTs and so on, are connected. In addition to that, there are optional local interrupts. And local interrupts can be used for heart-specific peripheral interrupts. So the difference between local interrupts and external interrupts is local interrupts only go to one specific heart, where an external interrupt would use something called a platform level interrupt controller to distribute interrupts to different devices. And we'll talk about that in a bit. Interrupts are also optionally per privilege level. In this way, you can have interrupts that are targeted specifically to machine mode, such as the machine external interrupt, but you can also have interrupts targeted at supervisor or user mode. So you can have user mode external interrupts, for example. So if I go and take a look back at the machine status register, bits 0 through 7 deal with interrupts. And these are your global interrupts enables per privilege mode. So user mode interrupt enable, machine mode interrupt enable, and so on. The previous interrupt enable fields encodes the state of the interrupt prior to taking the state change. And these bits are interesting because they can also be written to as well. And this enables you to turn on interrupts when moving from a higher privilege mode to a lower privilege mode. And the same is true for the previous privilege level as well. MPP, you'll see here in bits 12, 11, and 12. These bits also can be written to, and this is how you would change from a higher privilege mode to a lower privilege mode. And I'll talk about that in a little bit. When an interrupt does occur, one of the first things you'll want to do is read the machine cause register, or MCause, and this helps you identify what caused the exception. So the most significant bit of this register encodes whether or not it was an interrupt or an exception, and then the least significant bits then tell you what was the resulting either interrupt or exception. So in the case where it's an interrupt, bit 0 would tell you that it was a bit 0 of MCause, with an exception code of 0 in MCause would tell you that this was triggered by a user software interrupt. Or likewise, exception code of 11 would indicate that a machine external interrupt occurred. If the interrupt bit is set to 0, this means that a synchronous exception occurred. And then the corresponding exception code field can be seen on the table on the far right. And this would be such exceptions like load and store faults, environment calls, so if you use the eCall instruction, and various other exceptions. The interrupt enable and interrupt pending CSRs are the registers that you would use to enable or disable specific interrupts. And the interrupt enable and interrupt pending registers have exactly the same mapping. So bit 3 would be the bit that corresponds to the machine software interrupt enable, and bit 11 would be the bit which corresponds to machine external interrupt enable. And bits higher than 16 correspond to the various local interrupt enables for those optional local interrupts that we discussed earlier. Now, because the width of these registers are the same as XLN, so it would be 32-bit for an RB32 implementation, or 64 for an RB64 implementation. The local interrupts here, this would give you space for 16 local interrupts in a 32-bit implementation and 48 local interrupts per heart in a 64-bit implementation. The machine trap vector sets the base interrupt vector and mode of the processor. So the base vector is the address at which the handler will be located in memory. And then the mode, you have two choices, either direct or vectored. In direct mode, all exceptions and interrupts trap to the same PC, and that's the value that's placed in the MTVEC base register field. If you set this to vector, then each interrupt will trap to a specific location in the vector table, which is a combination of the MTVEC base address and the exception code of the interrupt. So when an exception happens, on entry into the trap handler, the RISC-V heart will save the current state. And specifically, it does this by copying the program counter into another CSR called the machine exception program counter to save the address, the location that that was interrupted. It also copies the privilege mode into the MStatus MPP register, and then the state of the interrupt enable into the MStatus MPIE, or machine previous interrupt enable register. At that point, it then sets the program counter equal to the MTVEC address, and then it disables interrupts by setting MStatus MIE to 0. At this point, the machine is completely in your trap handler and executing software. And so some typical pseudocode is on the right here for a normal trap handler. And so the first thing you might do in the trap handler is to push the register file. And then, as I mentioned earlier, you would read the most significant bit of the mcause register to determine the type of interrupt. And at that point, you would branch to either the interrupt handler or the particular exception handler which triggered the interrupt. After that, you would pop the registers back off the stack and then execute the mret instruction, or machine return instruction. The mret instruction does things similar to interrupt entry, but in reverse. So it copies MEPC into the program counter. It sets MStatus MPP into the privilege mode, and then it copies the machine previous interrupt enable into the MIE register. As you can see, this is also because all of these registers are writable, MEPC, MPP, and MPIE. And this way, you can also use the mret instruction to go from a higher privilege mode to a lower privilege mode. For example, if you set MEPC to the address that you wanted to enter user mode, and then the previous privilege mode you set to user mode, when you execute the mret instruction, you then enter your user mode at the address space you identified in MEPC. So if you look at this in real software, so I have a RISC-V assembly interrupt handler here on the left, where we're pushing, it's called trap entry. At startup, we'll push the register file into onto the stack. Then we'll call a C function called handle trap. And in this case, this is where we'll use C code to actually perform the interrupt service routine, where we read mcause and branch to the appropriate handler. And then upon returning from handle trap, we'll then pop the ABI registers back off the stack and execute the mret instruction. And you can see at the beginning here, prior to that, we would write the MTVEC register with the address of our trap entry function here. Now that's great, but pushing and popping registers and it simply can be a pain. So the good news is you don't have to do that. In RISC-V GCC, we implement the interrupt attribute. And this allows you to entirely write interrupt handlers in C code. So in this case, we don't have an assembly routine. We simply have the handle trap register, handle trap function. And in this case, we pass it the interrupt attribute. And at this point, whenever an interrupt is taken, the compiler has already taken care of saving and restoring the necessary registers on the stack, as well as any alignment requirements, as well as calling the mret instruction after popping the register file back off the stack. And you can see in this case, when we're writing to MTVEC, we simply write the address of the handle trap function. Now I mentioned local interrupts and how they're somewhat limited in the number of interrupts that you can have, but the good news is that RISC-V also has support for global interrupts. And global interrupts are defined as an interrupt which can be routed to any heart in a system. So in the case of a multi-threaded or multi-core design, you could have what's called a platform level interrupt controller, or PLC, which can be used to distribute interrupts to all the cores in the system. The PLIC would be specifically connected to the external interrupt signal for one or more hearts in an implementation. And if I take a look at the PLIC interrupt code, again, on the left here, it looks exactly the same as the previous example. The addition we added here is that we actually defined a machine external interrupt function here to handle interrupts generated by the PLIC. And in this case, the jump table would then jump to this function for interrupt code 11, which was the machine external interrupt. And then in the PLIC handler, we can read the PLIC claim complete register. And this is how we find out which interrupt was the highest priority pending interrupt at the PLIC. We can then use that information to branch to that specific interrupt handler. And then upon completion of that interrupt routine, we could write the number of that interrupt back to the PLIC, indicating that that interrupt was completed. This is what it looks like at a system level architecture, where you would have a number of global interrupts connected to the PLIC. I think the PLIC specification allows for over 1,000 interrupts, or 1024. And the PLIC would then be connected to the machine external interrupt of all the hearts in the system. So that'll complete the basic introduction to the RISC-V architecture. There are a number of resources available to find out more information on RISC-V. So the first would be the RISCV.org website. You can go here to learn more about RISC-V specifications, to actually download and read the specifications. It also has links to the mailing list if you want to join the mailing list or read the different threads on the list. It also has links to the workshop proceedings. This is a very valuable resource. So the RISC-V Foundation hosts 2 or more workshops per year, and all of the proceedings of those workshops are posted publicly, both in slide form as well as videos. You can also find a lot of information on GitHub. So there's the official RISC-V GitHub at github.com/RISC-V. You can find the specifications and software common to the RISC-V ecosystem here. You can also go to Sci-Fi's GitHub, where you'll find Sci-Fi specific software and SDKs. And then finally, on the Sci-Fi website, where you can find more information on Sci-Fi specific RISC-V IP, as well as our development platforms. We also have a number of tools that can be downloaded directly from our website, including binary distributions of the tool chain. We also have a pretty active user forum as well. Don't forget, this is just the first in a 3-part webinar series. So we'll have the second webinar next Wednesday at the same time, where we'll cover the Sci-Fi 2 series core IP in more detail. And then on May 23rd, it'll be more of a hands-on webinar where we customize the 2 series core using Sci-Fi Core Designer and take that all the way to Hello World using the software development kit that we have at Sci-Fi. You can register for these webinars at the URL provided here below. Okay, so there were a number of questions here, so I'll turn to the panel here and get some questions answered live. Okay, so first question, can RISC-V, RISC-V defines a 128-bit architecture as well, and does that support the compressed instructions? And the answer is yes. The RISC-V, the 128-bit specification, does also support the 16-bit compressed instructions. Okay, another question, in M mode, machine mode, would you need to have both MIE bit set in MStatus and the proper bit in the MIE register? And the answer is yes. So MStatus can be thought of as a global interrupt enable for a specific mode. And then the machine interrupt enable register itself would be the individual enables per interrupt. Okay, so which version of the Linux kernel has support for the RISC-V architecture? I believe the RISC-V was publicly accepted upstream in version 4.15 of the RISC-V Linux and 4.15 of the Linux kernel. And then there's a follow-on question of which boards or single board computers are supported in the Linux kernel. So Sci5 have a Linux capable board called the Hi5 Unleashed. This was released in February of last year, so it's been available for some time. So this is a quad core 1.5 gigahertz, fully coherent Linux capable single board computer. So you can go to our website and find links to actually purchase that board today. Yeah, by heart, we direct what exact, so the question is essentially what is precisely the definition of heart? So heart is short for hardware thread. So in the context of single threaded cores, a heart would be a core. So if you have 2 cores, then that's equivalent to 2 hearts. The ambiguity comes in if you have a multi-threaded core. So in that case, if you have a core with 2 threads, then you would have 2 hearts, but a single core. And that's where the difference comes in. All right, with that, I think we'll go ahead and conclude today's webinar. Thanks everybody for joining, and don't forget to sign up for the next 2 webinars on May 15th and May 23rd. Thank you very much.